Hello class, welcome to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today, in this lecture, we will discuss the different analogous systems, that is the electrical analogy of mechanical systems. So the points which will be discussed in this class are analogous system, the electrical analogous of translational system, electrical analogous of rotational system, application of force current, force voltage analogy, and the references. So first, start with the analogous system. In the previous class, we have learned the mathematical modeling of a system. Now, the process of obtaining of the desired mathematical representation of the system is known as the modeling. And a mathematical model is not unique to a given system. A system may be represented in many ways and therefore may have many mathematical models depending on it. The dynamics of many systems may be described in terms of differential equations obtained by using physical laws governing a particular system. And once a mathematical model of a system is obtained, then we can apply various types of analytical and computer methods for the analysis and synthesis purpose. Now, for the modeling of mechanical systems, we have learned that the motion of mechanical systems are generally two types. One is translational, another is rotational, or the combination of both. Now, if two systems are present which have the identical mathematical models are known as the analogous systems. That means both of the systems have the similar form of differential equations, as well as both of them have the same mathematical models, and the dynamic characteristics of both the systems will be identical. If these three obeys, then both the systems are called analogous systems. And in this lecture, we will consider the analogous systems of mechanical and electrical systems, and the vice versa. So, first consider the electrical analogous of translational systems, that is the force voltage analog. In this diagram, this is a mechanical translational system. Where this K is the spring, this one is the damper, and one mass is connected to it. Force Ft, that is the external force, is applied in this direction, and due to this application of force, displacement xt occurs. Now, according to the Newton's law, the total force F of T is the summation of the forces acting on the mass. So, F equal to m d square x dt square, that is the acceleration, plus b into dx dt. Dx dt is the velocity, plus kx, x is the displacement, and k is the stiffness coefficient of the spring, and b is the damping coefficient of the damper. Now, the electrical system we are considering here, as we are finding out the force voltage analogy. So, here we are getting the force equation, and for the voltage equation, we are considering a series RLC circuit. So, for the series RLC circuit, RL and C are connected in series with the supply voltage V, and I current is flowing through the circuit. So, if we apply KVL in this loop, then the supply voltage V equal to the drop across the R plus drop across the L plus drop across the C. That is the summation of all voltage is equal to 0. Now, we are getting this equation, Dt is equal to Ri plus L di dt plus 1 by C integration I dt. Now, we know that actually I is the rate of change of Q, that is the charge. So, I equal to dq dt, and we are putting the value of I equal to dq dt in the equation 2, and hence we obtain the equation Dt equal to L d square q dt square plus r dq dt plus q by c. Now, if we consider the equation 1 and equation 4 and compare these two, then we can say that when the force is analogous to voltage, here we obtain the equation of force and here we obtain the equation of voltage. So, force is analogous to voltage. Then by comparing that, the velocity in this equation is dx dt, and if we compare this with this equation, then dx dt is analogous to the dq dt, and dq dt is actually the current. So velocity is analogous to current. Similarly, for the mass in this equation, if we compare equation 1 and equation 4, then m is analogous to L. Here L is the inductance. So we can say in mechanical system, if we consider the mass, then electrical analogous of mass is the inductance. Now if we consider the viscous coefficient, that is B, then it will be analogous to the R, the resistance. And for the displacement X, we are considering Q, that is the charge. And for the stiffness coefficient K, if we compare this equation 1 with 4, then K is analogous with 1 by C, or the reciprocal of capacitance. So these are the force voltage analogy. Next is the force current analogy. That means we have to consider, for force, we have to consider the mechanical translational system, and the same way for mechanical translational system, the force equation becomes F equal to m d square x dt square plus b dx dt plus kx. Now, when we are using the current, then we have to consider the current source and the parallel RLC circuit. So for this circuit, we can say that total current I is equal to summation of all the currents to C, L and R. So if we apply the voltage across this in V, then we can say the current to the resistance R is equal to V divided by R. In the same way, the current to the capacitance is C dV dt, and current to the inductor is 1 by L integration V dt. Now we know the rate of change of flux is known as the voltage. So V is equal to d phi dt, and if we put the V equal to d phi dt, that is equation 3, in equation 2, then we can obtain the equation IT, that is equal to C d square phi dt square plus 1 by R d phi dt plus phi by L, and this is denoted as equation 4. Now we have to compare the equation 1 with equation 4. Here we are obtaining the force equation, and here we are getting the current equation. So if we compare this equation 1 and this equation 4, then we can say the force is analogous to the current I. Here we are comparing equation 1 and equation 4 because both have the same type of mathematical model, and the dynamic characteristics of these two systems are identical. So then for the mass m, we are comparing both, then we are getting mass is analogous to the capacitance. If we consider the velocity, that is dx dt, then it will be considered as d phi dt, that is the voltage. And if we consider the viscous coefficient, that is B, then it will be considered as 1 by R, that is known as the conductance. And for the stiffness constant K, that will be considered as 1 by L, that is reciprocal of inductance. And for the displacement X, we are getting that it is analogous to the flux. So these are the mechanical elements, and for these mechanical elements, the analogous systems of electrical are this way. Next is the torque voltage analogy, and torque is used for the mechanical rotational system. So we are considering here the mechanical rotational system, and in this mechanical rotational system, J is the moment of inertia, D is the damping coefficient, K is the spring constant, and application of torque, the theta is the angular displacement. So we can write the equation, torque equation, that is T is equal to Z square theta dt square plus B d theta dt plus K theta, where d theta dt is the angular velocity. Now we have to find out the relation with the voltage. That voltage can be obtained by the series RLC circuit, and for this series RLC circuit, the equation becomes Vt, that is equal to summation of all voltage drop equal to 0, and V is equal to drop of R plus drop of L plus drop of the C. So it becomes Ri plus L dt plus 1 by C I dt. Now I is equal to dq dt, that is rate of change of charge, and put the values of I equal to dq dt in the equation number 2, and we can obtain that Vt is equal to L d square q dt square plus R dq dt plus q by C. Now we are comparing this equation 4 with this equation 1, because this equation 4, this is also a second order equation and this is also a second order equation, and both have the identical mathematical model. So we can compare the equation 1, T is equal to Z square theta dt square plus d theta dt plus k theta with the voltage equation. And then we can say here in mechanical system we are getting the torque, and torque is analogous to the voltage. And when we are considering the angular velocity d theta dt, it is also denoted by omega, and it will be considered as dq dt, and dq dt means it is a current. So angular velocity is analogous with the current. For the moment of inertia J, we can say it is analogous to the L, that is inductance. Viscous friction coefficient B is analogous to the resistance R. The angular displacement theta is analogous to the charge Q, and the stiffness constant K, that is analogous to the 1 by C, that is reciprocal of the capacitance. Next is the torque current analogy. For torque current analogy, we will consider the mechanical rotational system and the parallel RLC circuit with current source. So in this section, we are getting the torque equation. T is equal to Z square theta dt square plus d theta dt plus k theta. And in the parallel circuit, in the same way, we are finding out the equation 4, that is C d square phi dt square plus 1 by R d phi dt plus phi by L. And as both are the same mathematical models, so we can compare this current equation with this torque equation, and we can say the torque is analogous to current, and then the J, that is moment of inertia, will be analogous to the capacitance. The d theta dt, that is the angular velocity, or omega, it also denoted as omega, that is same as d phi dt, and d phi dt means the rate of change of flux, that is the voltage. So angular velocity is the analogous with the voltage. The moment of inertia J, that is analogous with capacitance. Viscous friction coefficient B, that is analogous to the reciprocal of resistance. Angular displacement theta is analogous with the flux, and stiffness coefficient K, that is reciprocal with the inductance. So next we will consider the force current analogy. So in case of force current analogy, a mechanical circuit is given, and we have to find out the electrical analogous of this mechanical circuit using the force current analogy. So it is given that we have to use the force current analogy. So first write down the free body diagrams of three masses. So first, if we consider the M1 mass, then the force is acting directly on the M1 mass, and due to the force, displacement is x1. So where the displacement is in this direction, that means the inertia force will act in the opposite direction, and that is denoted by F of M1. Next, the K1 and B1 is connected to M1, and when due to that force x1 displacement have occurred, then B1 and K1 both are compressed, and for compressed, the force will be acting towards the body, hence the F of B1 and F of K1 are acting towards the body. And for the spring K3, when K3 is connected in between M1 and M2, so when M1 is going towards the displacement, that means K3 spring is also compressed, and due to this compression the action of the force will be towards the body, and hence F of K3 is towards the body. Now we can say all these are opposite of this force. So total force F is applied force F, that is equal to summation of these opposite forces. So we can write this equation F equal to summation of m1 d square x1 dt square, that is F of m1, plus for K1 is acting only with m1, so that is K1 x1. Next is K3. K3 is acting between these two, so we have to consider both the displacement. So it will be K3 into x1 minus x2, plus B1 is acting only with m1, so B1 dx1 dt. So this is the free body diagram for the mass 1. Next we have to consider the mass 2. When mass 2 is considered, then there is no external force directly linked with the mass 2, so the direct force is equal to 0. Now K3 is connected to the mass 2, so the equation will K3 will be acting towards the body. So F of K3 is acting towards the body. Next is B2 and K2, and when it moves towards the direction of the displacement, then again B2 and K2 are compressed, and due to this compression the force will act towards the body. So F of B2 and F of K2 is acting in this direction. Due to the displacement x2 in the right hand side direction, the inertia force F of m will acting opposite of this direction. So hence F of m is acting in the opposite direction. And for K4, again if it shifts to the right hand side, that means K4 is compressed, and due to this compression the work force will be acting towards the body. So F of K4 is acting in this side. So the total force F of K3 is equal to summation of all this, or we can say write down this equation as m2 d square x2 dt square, that is m2 plus K3 for K3, that is equal to x2 minus x1. As we consider the K3, so in this case the displacement of x2 is first considered and then the displacement x1, plus for the K4 it will be K4 into displacement for this same block x2 minus the next block x3, plus for this B2, that is B2 into dx2 dt plus K2 x2. So we can write down this equation. And next the free body diagram of M3. For this M3, similarly we can say that F of M is acting in the opposite side and only K4 is connecting to it. So summation K4 is K4 into x2 minus x2 plus M3 d square x3 dt square, that is equal to 0. Now we are getting the equations from the free body diagram, equation 1, equation 2 and equation 3. Now we have to use the force current analogy, and we have to replace all mechanical components of equation 1, 2 and 3 with the electrical quantities respectively. Now when we consider the electrical quantities, that is the for force current analogy, then force is replaced with the, first consider the equation 1. So this equation, force is replaced by the current I, the velocity is replaced by the voltage, the displacement is replaced by the flux, mass is replaced by the capacitance, the viscous coefficient is replaced by conductance or the 1 by R, and stiffness constant is replaced by the 1 by L. So after that we are getting this equation 4, and from this equation we can find out this circuit, because the supply is IT, so I is given, then the voltage are the V1. So we have considered a node V1, and for V1 the resistance is connected to V1, the C1 is connected to V1 as well as L1 is connected to V1. So these are three parallel paths connected to the voltage V1. And another one is L3. L3 is connected between two voltages V1 and V2. So we have considered V1 and V2 over here, and L3 inductor is connected in between V1 and V2. Next we have to consider the second equation, and for the second equation again we are putting the analogous systems of the mechanical systems using the force current analogy, and we are getting the equation like this. So for for this equation we can say that here there are three voltages V1, V2 and V3. So for V2, look at the V2. V2 is connected with 1 by R2, C2 and L3. So not L3, that is for V2, that is 1 by L2. So this L2, this C2 and 1 by R2 all are connected in parallel with the node V2. And in between node V2 and V3 there will be an inductance L4. So in between these three are same node, that is V2, and in between this V2 and V3 L4 is connected, and similarly for V2 and V1 L3 is connected. So in between V2 and V1 L3 is connected. So like this way we can form the electrical equivalent circuit from this equation. And for the third equation, we can again replace the mechanical systems by its electrical analogous system using the force current analogy, and we are getting this equation. And look at here that there are two voltages is given here, V3 and V2, and in between when V3 and V2 the L4 is connected. So L4 is connected in between V2 and V3, and for the V3 only the C3 is connected. So this capacitance is the C3. Now if we combine the three equations, that is equation 4, 5 and 6, then we can find out the complete circuit like this, and this electrical circuit is analogous to this given mechanical circuit using the force current analogy. Next, consider another example, an application of force voltage analogy. Now we have to draw the electrical analogous of the given mechanical circuit where M1 and M2 is connected, and in between M1 and M2 damper B1 is connected, and B2 is connected with the M1 only, and K is connected with only M2. And due to the force applied at the M1 at downward direction, the displacement of M1 is x1 and displacement of M2 is x2. Now, if we consider the free body diagram for M1, then we can say the force is applied in this direction and x square is downward. So the B2 it is connected to in this way, so it will be expanded, and for this expanded it will go outward of the body. And B1 again it has been expanded, so it will also go outward of the body. And for the inertia force, that will opposite of the displacement, so it is also out of the body. So the total summation of Fm1, Fb1 and Fb2, that is equal to total F, and we can write down the equation F is equal to m1 d square x1 dt square plus b1 dx1 dt minus dx2 dt, because b1 is connected in between m1 and m2, and plus b2 into dx1 dt. Then we will rewrite the electrical analogous by using the force voltage analogy. That is, force is analogous to voltage, velocity is analogous to current, mass is analogous to inductance, viscous friction coefficient is analogous to resistance, displacement is analogous to charge, and the stiffness constant is analogous to 1 by C or reciprocal of capacitance. Then we can rewrite this equation like this: B equal to R2 into I1 plus L1 di dt plus R1 I1 minus I2. So from this equation, this is a voltage equation, and we can use that there is a loop, and in that loop V is the supply voltage. So I have written here V, and for I1, if I1 is the loop current, then R2 is connected to this I1 only. So R2 is connected over here, and L1 is connected to I1 only. So L1 is connected over here. And for the R1, that is connected in between two loops, I1 and I2. So I1 is another one loop, and there will be another loop, that is I2 current. So we are considering next the free body diagram for mass 2. And for the mass 2, the K is connected over here. So F of when it goes to the displacement direction, then K is expanded, and when K is expanded, it goes upward force, that is F of K. And the inertia force F of M will act in the opposite direction of x2, and for the B1, if it goes downward, then it is compressed and it will give the reactive force towards the body. So hence F of B1 is in this direction. So all these three are equal to 0. So this force is equal to, for M M2, the summation of these force is equal to 0. And for this, we can again rewrite the electrical analogous, and it becomes 0 equal to Q by C plus L2 dt plus R1 I2 minus I1. So for this one, we have to consider the second loop current I2, and we can say that I2 minus I1, that means R1 is in between the loop 1 and loop 2, and L2 is connected to the second current second loop, and this one is 1 by C into charge, that means 1 by C into Q. So combining these two electrical circuits, we can find out this electrical circuit which is analogous to the given mechanical circuit using the force voltage analogy. So using this type of force voltage analogy and force current analogy, we can easily find out the electrical equivalence of the mechanical circuit or the mechanical analogous system of the electrical circuit. And these are my references. There is a Kastiko Ogata, that is Modern Control Engineering. It is a book, and another one is book by Harim Asfaq. So thank you.